Okay. Everybody ready? Yeah. Do you have AC? Okay. Okay. Everybody ready? All right. So, how is the homework? So let's review. But everybody's homework sort of okay. A little tricky, but okay. All right. So let's answer this question. Everybody went home and they thought about it all night. So remember this from Friday night. So Friday night, I gave you this program. Remember, it was the program where we were solving equations on a grid. It was a 2D grid. We updated all the variables, all the cells, and then we weighted, we barriered, and then we updated all the cells again, and so on and so on. And last time we talked about why there were 3 barriers. Does everybody remember this? Okay, so we said that this one makes sense because this barrier, after the barrier, the program checks to see if it's done. So this code adds up all the sums, all the differences. This code checks to see if it's done. And if this barrier was not here, then some thread might check to see if things were done before all the threads added up their part. And then this barrier was here because one thread might say, we are not done. Go to the top of the loop, set this variable diff to 0, and then all the other threads would say, oh, we're done, and quit. On Friday, we did not talk about why this barrier was here. So did anybody think about why this barrier was here in the code? Why is there a third one? What can go wrong in my code? What bug can happen if I take out this barrier? So some thread sets diff to 0, starts running. Some other thread says we are not done, moves to the top. The first thread has already added back into diff. Second thread sets it to 0 halfway through, and then the value of diff is not correct. So that's why the third one is here. Okay. Did anybody figure out how to do this with one barrier? Any ideas? No ideas? So here was the code that I have on the slide. This is correct. And there's only one call to barrier now. So only one synchronization, one time we stop. So look at what this code does. I actually have 2 different diffs, or 3 different diffs. And so every time we go through the loop, we are adding to one of the diffs. So the first time through, we add to diff 0. The next time through, we reset diff 1 and add it to diff 1. So that every time we stop at the end, but we don't have to worry about one thread setting the value to 0 while other threads are writing to it. So if you look at it here, the difference is we accumulate. We add into diff index. And diff index goes from 0 to 1, so 0 to 2, 0 to 1, 0 to 1, 0 to 1. So when in iteration I, the threads are looking at diff 0. In iteration I plus 1, the threads are adding into diff 1. So this is a common technique. If you have 2 people needing the same thing, just create 2 of them, and you can eliminate the synchronization. So in the original code, I had to wait for every other thread 3 times. Now I only wait for every other thread once. So this is a more efficient piece of
There are
code.
three threads.
Well, there are n threads. There can be many threads. Yeah. Okay, I'll let you think about that a little bit. Okay, so let's get to today's lecture. So today's lecture, I want to talk about scheduling work. So last time, well, the first time was about how hardware works. And you guys are thinking about that in your homework now, in your assignment. Last time was about how to think about writing at the beginnings of a parallel program. And this time will be about how to optimize its performance. And specifically what I want to talk about is I want to talk about techniques for dividing work up onto processors so that everybody gets the same amount of work. So our goals are to balance the workload onto all of the processors, all of the execution resources. So I have all of these things to do. I have a couple of workers. I need to make sure that all workers have the same amount of work. And I don't want to spend too much time figuring out who does what. Because if I spend too much time figuring out what processor does what work, that's just wasted time. So I don't want to do that. Okay. So here is my first tip. So most students in this class, I will give them a problem, and they will think of many complicated ways to solve the problem. They will think of a fancy algorithm, they will think of a very sophisticated piece of code, and I strongly encourage you, maybe not on assignment 1 because you don't write much code, but on assignment 2 where you have to solve a problem, always do the simplest thing first. So for those of you that have done part 1 of the programming assignment, where it asks you to figure out a performance problem. So we ask you to run the code, make measurements, and from the measurements, figure out how you can do better. That is part 1 of the homework assignment. And what some people do is they write a very complex algorithm, and then they run it. And a much simpler algorithm would have been just as good. And this will happen to all of us. It will happen to you, it happens to me, it happens to my students. We always don't do the simplest thing first, and it's a very inefficient way to work. So whenever you get a parallel programming problem, I want you to think about the first thing I'm going to tell you today. And only if that doesn't give you good performance, then we can go to the more sophisticated things. So let's talk a little bit about scheduling work onto workers. So the goal, what we want to try and accomplish, is if I have, let's say, 4 processors, and I have a bunch of work. So I'm going to call each one of these pieces one piece of work. Your goal should be for the entire program, you want all of the workers, all of the processors, working. Because if you don't, that means that one of your workers is not doing anything for some period of time. So we had that problem with 4 students here on the first day of class, where I gave one of the students much more work to do than the rest of the students. And the other students were just waiting, looking at you to finish your work. And so that's what I drew here. So here I gave P4 one extra thing to do. And notice that at the end of the program, processor 1, 2, and 3 have nothing to do. So if processor 1, 2, and 3 have nothing to do, that means that this part of the program is like a sequential program. And if it's like a sequential program, remember the graph from last time. I said that if 1% of your program is sequential, if you have a computer with a lot of cores, you can't get a very good speed up. So in this example, I might think I did a pretty good job, but out of 1, 2, 3, 4, 1, 2, 3, 4, out of 17 pieces of work, 1 out of 17 is sequential, which means that's about 7%. 7% of this program is sequential, and so the maximum speed up is going to be notably limited. Okay, So if I gave you n pieces of work, like the number, the variable n, so you have many things to do, and I said you had 4 processors, what is the easiest way to assign work to the processors, hoping that it will be equal? How many pieces of work does every processor get? N divided by 4, right? So if I knew I had n things to do, and I had n workers, all of my students are workers, I would take n divided by number of workers, and I would give everybody that amount of work. So that's what we did last class. We had all of the pieces of work, or all of the dots, all of the elements. And we said we had 4 processors. So I divided the work up by 4 and handed 1/25% of the work to every worker. And there were 2 different ways we talked about doing it. But in both cases, I said, I'm going to predict that all of the work is the same cost. And since all of the work is the same cost, if I just divide up the grid, that should give equal work to all my workers. So if I say the words static assignment, this is what I mean. I mean, before I even run the program, I'm going to decide what work, what tasks get done by what workers. So I'm not making any decisions as the program runs. I'm making decisions before I start doing it. It's like I say, we have to do some stuff. Okay, you guys do some stuff, you guys do some stuff, you do some stuff. So here's my question, and I'd like to hear your thoughts, is when do you think it's possible to do this? And I like to use the word predictable, because the reason why this was okay was because I know, or I'm assuming, that computing, updating every cell, every dot, is the same cost. If some took a lot more time than others, this may be a very bad partitioning of the work. So I can get by with static assignment, because it's the easiest thing to do. So if this works well, I want to do it. I can get by with static assignment when the cost of the work is predictable. So one example of when it's predictable is, well, I know that it's all the same cost. It's all the same cost. So here there are 12 tasks. And of those 12 tasks, they all have the same cost. I have 4 processors. I give each processor 12 divided by 4, 3 things to do. Completely equal. Now, could I do a static assignment if the pieces of work were of different size? So imagine I gave you a homework problem, and I said, all of the tasks are a different size, and I gave you all of their sizes. So I gave you how much cost every single one was. Do you think you could divide the tasks among the processors and still get an even workload balance? Or very close to an even workload balance? No? So let's say that the tasks were of these sizes, like this, all different sizes. But you know the sizes. You know that before you start running your program. So it would have been possible for you to say, okay, well, let me compute the sum of all the work. Let me divide the sum by 4. And let me assign tasks to the processors until it is about 1/4 the work. And then I go to the next processor and assign these. So this thing is this box. This thing is this box. This thing is this box. And so I have divided all the work across the processors, and it's pretty equal. So the work doesn't have to be the same cost for me to be able to divide it up very efficiently. I only need to know what the cost is. Or I might need to know statistics of the cost. For example, if I knew the average cost, then I might feel okay with giving an equal number of work to all the workers. So what do you think I can do? All of these ideas assume that you know how expensive everything is before you run the program. And assignment 1 has many examples where you do not know how expensive processing an element is until you actually do the processing. So in part 1 or part 3 with the fractal, it has to iterate a bunch of times, and you don't know when it would stop. In part 4 with square root, how much work you do depends on the value of the number. So you don't have any idea of how long it will take. So if I don't know the size of these blue boxes, how could I take a different approach to making sure that everybody gets the same amount of work? What do we think? So why don't you talk? So while we have some time, this lecture will probably be a little shorter today. Come up with an idea with the person sitting next to you, and now you do not know how much work there is ahead of time. So take 1 minute, really quickly. Okay. So, what do you think? What would be one algorithm for you have no idea how long this box is when you start to run it, and you know you have a bunch of pieces of work? How can you make sure that all of your threads, all of your processors do about the same amount of work? What did you come up with?
Run every piece of work in time.
Oh, I see. So your solution is to run a little bit, and then move to something else, and then run it a little bit. That would probably work, sure. And so you say you give the first 4 to the processors, and you run a little bit. So then what would happen here when this one got done? What is your approach there? Okay, you think about it a little bit. I think you could make that work. But so some other ideas? What? Okay, well, no. Can you help me think? Okay, go back. No, not in the front. The people in the front are paying attention. We want to go to the back. Okay.
What do you think? Just
yeah. So what do you think? Yeah.
For example, if one task is completed, the task just help other tasks.
Okay. And so one way to think about it is, how about we just put all of the tasks in a line? We put them all in a queue, or really, we put them all in a line. And now what every thread is going to do is it will just take the next person in line, do that, and then when it's done, like you said, it just goes back to the line and gets the next element. So your solution was probably even more complex than mine, because you were saying it could take it from somebody else. But I'm even going to go even simpler. We're just going to ask all of the work to get in line. And every worker, when the worker has nothing to do, the worker goes to the line, tells the person in the front, I want to work on you. And then that's how all the processors will always be doing something until there's nothing else in the line. Okay, so let's talk about that in this, right here. So this is what I did. So I wrote some code, and that's exactly what I did. And it uses exactly what we just talked about. And let's look through it. So imagine that I have a piece of code. This is just regular C code. And let's say that my task is to compute if the number x of I is prime. So this is a task that you don't really know how long it's going to take. Because if we did, a lot of the world would be very different. Right? So here's a task that has unknown cost. I guess we know it's cheap if it's even, but after that, it's too high. So we want to do this for all of these numbers. And now I want to run this code in parallel. So there's a list of numbers, there's a list of results, and the program for every number computes if it's prime, and if it's prime it writes true, else writes false. Okay, so this is my parallel version of the code. So it's very much like this line that I told you about. So imagine that this code here is being run by all of the processors, or all of the threads. So the first thing to notice is that there's a while loop. So that's what I said is while we're not done, while there's work in the line, I need to keep going back and doing more work. So while not done, keep doing work. And then this is one of the most important variables in the program. So the counter is saying, what is the next thing to do in this case? So the counter starts at 0, meaning you need to go get the first thing in the line. In fact, we were having Chinese food and we all had a counter last night when we were waiting for food. Is they said, okay, the next person that needs to do work and doing work with eating Chinese food was the next person in line. So this thread increments the counter. So it's like taking the ticket. It says, okay, the next person in line is 0. I will grab 0 and make the next person in line person 1. And then since I grab 0, I'm going to do the work for is prime 0. Well, yeah, I equals counter plus plus, okay? So I grab the value of the counter, set I to it, and then I do that work. And only when the counter gets to n, or is greater than n, do I stop. So I'm going to keep going back to the line, and I'm going to do more work. And if I get the number, an even number, I finish my work very quickly and I go back to the line. Because I can test whether it's prime very quickly. If I get a very, very large number that maybe is a 64 or 128-bit number, I may not come back to line for 2 weeks. Now, remember last class we talked about why we needed a lock here. So what could happen? What bug could happen in my program if I do not put a lock around counter plus plus? Or if I said it differently, what would happen if the read of the counter and the update of the counter, add 1 to it, is not atomic? So why does this need to be atomic? So let's call him somebody, some other person. Yeah. Why should the counter? I know you probably know the answer to this question.
Maybe 2 programs will do 1 work.
Want to do the same piece of work, exactly. So I'm going to go ahead and draw this out one more time so everybody knows. So imagine the counter again is, let's pick a number. Let's say that word. Okay. So let's say the counter is, I don't know, the number 10. Right? So I'm a thread, and I'm going to read the value. I read 10, so I say, oh, I need to do piece of work 10. And now I want to update it to 11. But let's say Yan is another thread. So Yan will come up to the board, and he'll read 10. And right before I make it 11, he'll read 10. And that means we both have piece of work 10. And then that's not good. And what will happen is that I will write 11, and you will write 11 as well. Again, so we will double up the piece of work. So we need the read of the value and the write of the value to be atomic. And by atomic, it means nothing else in the system can happen between the read, I get 10, and the write of me making it 11. So here's the question. So I said it needs to be atomic, and you're nodding your head because that's true. But this is lock, unlock. So here's the question is, why is it true, it's correct code, that this read and the write is now atomic? Because I put a lock and unlock here. I didn't tell the compiler, make this atomic. I used two commands. I used two API calls, lock and unlock. So why do I know? Why am I absolutely certain that this code is correct? Why is it not possible for Yan and I to both read the value 10? So when one thread takes a lock, what does that mean about all other threads? Can somebody help me with that? Say? Yeah, it tells them that they have to wait until it's unlocked. But let's think in terms of properties. If one thread has the lock, no other thread can have the lock. Correct? So if one thread has the lock, that means that, and if the rule is that no thread can get past this command unless it has the lock, it means that if I as a thread are in between lock and unlock, I know that no other thread is in between lock and unlock as well. So I have a guarantee that this thread, the thread with the lock, is the only thread between lock and unlock. And since I was careful that the only update and read of the counter variable is in between the lock and the unlock, I know that this is atomic. There's nothing preventing me from reading counter up here, but my program would be incorrect. So if I had so does everybody see why that lock is there? The lock is there to prevent multiple threads from accessing, reading, or writing counter at the same time. Only one thread can. And since only one thread can read and write counter at the same time, then the read and the write are atomic, because I know that they happen together. There's no way for me to read, release the lock, and then write. So what this code has done is this code has essentially, I don't have a list data structure. I don't have a standard vector or a standard list. But what my code has done has essentially put all the work into a list. And all the threads just take the next element in the list. That's what this code is doing. Okay. So now this is good. So I'm calling this dynamic assignment, because the assignment of what thread does what work is not determined until the program starts running. Because if Yan got a long piece of work that took a really long time to test primality, I might have done a whole bunch of tasks in that amount of time. So what work I do and what work Yan does is not determined until we just run the program. So it's very dynamic. Okay. But there's a performance problem with this implementation. There's something, so what's good is that all of my workers are now doing about the same amount of work. That's good. No problem. So there's no workload. Let's assume that there's no workload imbalance. But there's a problem here in that, for example, many primality tests will be pretty cheap to test. And sometimes this lock is not very cheap to actually acquire, because I'm not going to talk about how we implement a lock today. But you could imagine if Yan and I were up here, we would kind of have to be communicating. I would have to say, do you have the lock? He'd go like, no, go ahead. And I'd go, okay, sure. And then later he would say, hey, do you have it? I mean, yeah, like I still have it, please wait. And then he's like, do you still have it? I'm like, yes, I still have it, please stop bothering me. And then finally, he might say, do you have it? I say, no, go ahead. So you can imagine that the lock and unlock has a good bit of communication between the threads, and it can be a little expensive to communicate between these threads. So in this program, one piece of work, one task, is testing whether or not one number is prime. That's what one piece of work is. And if I had to draw this, I'm going to draw this where in blue, for one thread, this is time going down. Time is going down. So blue is actually doing useful work. It's computing whether or not something is prime. White is time spent between Yan and I just talking to see who has the lock on what I should do next. And so as you can see, the problem with the dynamic scheme, since we just didn't up front say Yan is going to do the odd numbers, I will do the even numbers. That would be a very bad example for this case. But is that I'm now doing work to synchronize that I would not have done in the sequential program. So even though my program is perfectly balanced on all the workers, because I'm doing a whole bunch of extra work, my speed up may not be as good. And if the white bars happen to get bigger than the blue bars, my speed up could be quite bad. Very bad. So the question is this a problem? Well, this is a problem. It's not a problem if the cost of this function is extremely high. Because if the cost of this function is extremely high, that means the blue bars are very big. But if the cost of that function is extremely low, well, maybe the white bars are quite a lot of time. So with your friend now, I want you to take 1 minute, and I want you to tell me how you would change this code to make it more efficient if I told you that this function was very cheap and that you were unsatisfied with all of this time in white that was taking a large fraction of your program. And in fact, I showed you an example last class when I was spotting the p-threads. Remember, it was like 100 times slower or something like that? That was like these white bars were like 100 times bigger than the blue. Because in that example, the cost of creating the thread was high, and the cost of the function that we were calling was 0, because it was just called the empty function. Okay, so with your friend, I want you to, what is the simplest possible change to the code? You can basically change like 2 lines of code, 3 lines of code, that can make this way more efficient. So take 1 minute and talk it over. Okay, let's see. So yeah, why don't you call it? We'll go over here. Yeah. So what do you think? What would you do?
We can calculate multiple elements for a single task.
I like that idea. So right now, one task, one piece of work is one element. So right now, what I do is I compute 1 prime, go get the log. 1 prime, go get the log. So a very simple solution would be to move from counter plus plus to counter plus equals some other amount. And here I set some other amount to 10. So now as I go say, I want more work, and I go get the next 10 things, and so I spend more time over here doing that. And then I go back and I say, I want some more work, and I get 10 more things. So it's basically one line of code. The only complex part is right here. And this is just, I say for I for the next 10 things, except I had to do a min because I don't want to run off the end of the array at the very edge. So I made it 10. Why not? Maybe we should make it bigger. Because if 1 was inefficient, 10 is more efficient. Well, maybe 100 is even more efficient. Or what if I set this value to n? What happens if I set that value to n? Because bigger is better. 10 was better than 1. Maybe n is better than 10. So what is the problem if I set the amount of work I get to all of the list, or all of the line? Yeah, it's not sequential again. I have complete worst workload balance, but I have the lowest overhead. So there will always be a trade-off between you would like to keep your task size small so that you get good balance. You would like to make your task size big so that we don't spend most of the time just talking to each other. And there's not a lot of theory here. Basically, this tends to be pick a number, and if it seems too small, make it a little bigger later. And that's about as principled as one can be. But what would be the smallest number you would choose? Let's say if you had 4 processors. It wouldn't make sense to have less than 4 things to do, because then you're not using all your processors. So usually a good rule of thumb is maybe about 8 to 10 times the number of processors that we have. So if I have 4 processors, usually I like to make 60, 100 things to do. If I have 32 processors, maybe I go make a couple hundred things to do. And that just means that no one task can be too big, so it's unlikely to be imbalanced. So here's one more question. Let's say I take the algorithm that I just did. I like my value 10, works great. Do you think that the program will get good speed up if I give you task sizes? So this is task 1, 2, 3, 4, 5, 6, 7, n minus 1. Talk to your friend and figure out what problem could happen and how would you fix it. There is a performance problem if I run this code on work with these sizes. What can go wrong? So take 30 seconds. Okay. So first question is, what is the problem? Let's call it something. What problem did I just create?
The last task is to
So let me draw it for everybody. So I used the algorithm on the previous slide, and I assigned this task to processor 0, 1, 2, 3. Probably this one got done first, so that would lead to 0, or whatever. So I assigned the work to the processors that way. And then the last thread to get a piece of work got one. And it took a really long time. So there was no other work left in the list, but the longest task came last. And so whatever thread got unlucky and got the last task, in this case, processor 4, was working for a very long time, and the first 3 processors ran out of work to do. Okay, so if you knew the sizes of the tasks, what could you do? Right, we could change the order. We can say we're going to run the biggest tasks first. And so look what happens when I do that. Processor 4 ends up getting the big task. But it's okay, because the big task is not longer than sort of all the work that everybody has to do. So processor 1 does 1, 2, 3, 4, 5 things. Processor 4 only did 2 things. But no problem, everybody is busy all the time. That's as good as I can do. That's as good as I can do. But we had to know something about how expensive the tasks were to do this. So you'll find that when you're scheduling, if you know something about what you're scheduling, usually you can come up with a much better scheduling algorithm. Okay. So before I stop with the first session, I did want to say that in many applications, solutions combine both the techniques. They combine the idea of static partitioning. You do this, you do this, you do this, with the idea of I don't know how expensive everything is, so everybody get in line, or maybe I'll adjust, I'll reassign work. And 2 good examples are in scientific computing. So this is an example of simulating stars. And so there's different densities of stars. So here there are not very many stars next to each other. Here there are many stars next to each other. And you can imagine that one way to parallelize this application would be to cut the space into equal numbers of stars per space. But this is a simulation, so the stars move. And so the stars might clump up over here, and if you divided space this way, that may not be a very good division. So one answer would be every single time you need to perform the computation, you figure out exactly how to split the work. But this is a real-world simulation, and the stars move very slowly. So what these simulations often do is they statically partition the work. They run it. And after a while, if it ever gets not balanced, they stop the simulation and rebalance it completely. Another example is this simulation, where this is an airplane wing. And this is the grid of the fluid, the air around the airplane. And so around the wing, you want higher resolution, so you spend more cost around the wing. But as the airplane flies, the places where you need resolution might change. And so the mesh might get recreated from time to time in the various, as the simulation goes. So I just wanted to point out that even though I said there is static assignment and there's dynamic assignment, of course you can combine and mix and match all of these things as much as you can. Okay. So one thing that I haven't talked about yet is if I go back to this example. When I said that there was overhead, like when Yan and I have to communicate, I'll come back to this in a second. Okay. So, the reason why we changed our code to do 10 things at a time was that I wanted to avoid synchronizing with Aaron. We don't like each other, we don't want to talk very much. It's a waste of time. I don't get anything out of it. I need to be doing my work. Okay. So one solution was that we were fighting over the same variable. So we said, well, we can fight less if we only need the data every once in a while. So one list, we only touch the list a few times. Another answer could be just like how we fixed the barrier problem. We fixed the barrier problem by making multiple diff variables. We could fix the fighting problem by saying, Yan has his list, I have my list. We're not going to talk to each other unless my list becomes empty. So I'm going to have a list. He's going to have a list. We're going to do our own work. And only if I run out of work, I'm going to go over to Yan's list. And I'm going to say, I'm going to take this because I need something to do. Okay. So one answer would be to move from one queue, so I'd have to jump forward, to many queues. So every processor has its own queue. And I'm going to talk now in the second lecture today about how we can implement a system that actually has multiple queues. Okay, so the summary of the first part is that the challenge is achieving good workload balance. I want all of my workers to always be working. And I do not want to waste too much time figuring out who should do what. Because if I waste too much time, that's going to be hurting my speed up. Okay, so now I want to talk about a little bit more sophisticated version of scheduling. And in fact, it's sort of some of the ideas that you hinted at earlier. Okay, so far in this class, we have kind of seen two types of parallel programs. One type of parallel program was for each. For every piece of data, do something in parallel. So the example with the primes was that. The example of the solver last class was that. The example of the Taylor series was that. So I often refer to that as data parallel, meaning the reason why it's easy to run in parallel is that every piece of data can be processed independently. And we saw that with for each. You will see that if you haven't yet with ISPC tasks. When we get into GPU programming, CUDA runs that way as well. And there are many programming languages that allow you to say, here are many iterations of a loop. You can do them in parallel if you wish. So that's one way to think about parallel code. Another way to think about parallel code is just to create threads for processors. So I've shown you some code that looks like this as well. It's for every processor, it's going to create a thread. And that processor is just going to do whatever it's supposed to do. But now I want to talk about a new way to kind of think about a parallel program. Because some parallel algorithms don't necessarily say, here's a loop, go do everything in the loop in parallel. Other parallel algorithms, for example, divide and conquer algorithms, they're very parallel. But they expose the parallelism over time. So what I have on the board is quicksort. So has everybody seen quicksort at some point in your algorithms class? So everybody sees this sort. So okay, good. So I'm not going to explain it too much. But I'm just sorting a list of numbers between begin and end, the size of the, if the list is non-zero, so if the list is 0, I don't do it, or the list is size 1, I don't have to do anything. It's sorted. If the list is greater than 0, I'm going to pick one number in the list, and I'm going to divide the list into numbers less than that number and numbers greater than that number. So I'm picking, partition is just picking some element from the list and partitioning all the integers to, there's one group called begin, which is the list from begin to middle. And then there's another set of numbers between middle and end, and that's all greater than the value middle. Okay? And then I can just I can use recursion. I can now sort the left side, and I can sort the right side. Quick review of quicksort. So every time you call quicksort, you get two parallel things to do. You can sort the left sublist completely independently from the right sublist, and you get a sorted list. Okay, so these two calls, the quicksort, could be done in parallel if I wanted to. Now, do you think you can run quicksort on a machine with 8 processors? Because this code only has 2 parallel things to do. So is quicksort not a parallel algorithm, or is it a parallel algorithm? Who thinks quicksort is a parallel algorithm? And when I say parallel, I mean I want it to run on a machine with 8 or 32 processors. So some people think it's a parallel algorithm. Who thinks it's not a parallel algorithm because there's only 2 parallel things to do, so that's not enough parallel work to fill up 32 cores. I only have 2 parallel things to do. So if you wanted to run quicksort on a parallel computer with many cores, how do you get 32 things to do? 32 independent things to do. Yeah? No? Let's see. So who can help? So if one step gives me 2 things to do, how can I get 32 things to do? Each of those things creates 2 things to do, and each of those things creates 2 things to do. So I have to somehow, the parallelism comes slowly, unlike my for loop where all the parallelism was there. So this is your standard, regular divide and conquer algorithm. And every time we divide, we get more parallelism. So I'm going to give you, I'm now going to introduce a new parallel language. It's the 3rd one that we've seen already in class. But it's called Cilk, and this is a very popular parallel language. So this is present in any C++ compiler you have today, or at least if it's maybe not the one installed on, we may need to install on UGCC. But Cilk only has 2 things in it, and they're designed to help you write parallel divide and conquer algorithms. So there's 2 ideas. So normally, I'm going to jump ahead for a second. So normally in C++, if I call a function, so if I'm a thread, I'm working, I'm running my instructions. I'm running, like, let's say part A of my function. And then if I call another function, what happens? Control on this thread moves to that function. We go to foo. We execute all of foo. And then when foo is done, we go back to the original function and keep going. So it's all completely in sequence. So we would run part A. Oh gosh. That's not right. One second. Foo. Bar. Okay. Now, okay. So we would run part A, then we run foo, then we run bar, and then we run part B. All in one thread, completely sequential. That's what a function call does. Everybody, you all know that. You've done it 100 times, or thousands of times. Okay. So I'm going to change only really one thing. If we're going to call foo, we can put a term in front of it, and we're going to say spawn foo. And technically it's Cilk spawn foo because the language is called Cilk. So if we call a function, what that means is this thread now needs to go do that. And then when it's done with that function, it will keep doing what it was doing. Spawn foo means foo can be implemented in parallel with the current function. So if I'm running my thread and I say spawn foo, foo might start running and I keep going as well. That's the difference between regular function call and spawn function call. And that's the only change. That's the only change in this system. There's one other thing called sync. And you can think of sync like join. Sync says if I have spawn foo, and later on I say sync, I just wait for foo to finish. So if I wrote spawn foo followed by sync, that would be just like a regular function call, right? Because I spawn foo, and then I wait for foo to be done, and then I continue on. Right. But now I can do this. I can say spawn foo bar sync, which means I can spawn foo, do bar, and then say, hey, is foo done, and then wait for foo. So it's a little bit different. So I like to draw, if you want to think about it like threads, you can think about spawn as like fork or create thread. And you can think about sync as join on thread. But there's a big difference. Creating a thread means creating a thread. Like if I create a thread, that thread is now running and it's running in parallel. So spawn says the language, the runtime, the system can decide whether or not it wants to run this in parallel or not. So it may implement spawn foo just like regular foo, or it may implement spawn foo by having some other thread do foo. So if this is the way, it's an easy way to draw regular programs. Now I'm going to draw the dependencies for Cilk programs. So I'm drawing a line as a thread. And whenever I spawn something, I'm going to spawn another line out. And that doesn't mean that these are running in parallel. It just means that they do not depend on each other. And we could run them in parallel if we wanted to. So Cilk spawn foo bar Cilk sync says that the original thread spawns foo, calls bar, which is a regular function, and then waits for foo to be done. Cilk spawn foo, Cilk spawn bar sync is actually the exact same amount of parallelism as the first thing. But now we spawn foo, spawn bar, do nothing at all, and then just wait for the sync. So both the first version and the second version have two independent things to do. And of course I can do this a lot more. Spawn foo bar fizz, do buzz, and then sync. So buzz gets done on the original thread, it's a regular function call. All the other functions are spawned off and can be done in parallel. Can be done in parallel. So does everybody understand what Cilk spawn means? Now we're going to talk about how to implement Cilk spawn. We're going to talk about how Cilk is implemented. What? Well, okay, so this is a very important slide. If I ask you, what does this mean? You should answer the question to me. It says, I want you to spawn foo, which means the system can run foo in parallel with the calling thread if the system chooses to. So essentially putting spawn in front of a function call says that the execution of this function is independent of the calling thread. That's all it says. If this was spawn standard lib thread, that would say it's independent and is running concurrently. Those are two different meanings, right? So the rest of this lecture is going to be about when to choose. When should we run this in parallel? And when should we not? Okay, but this is an implementation decision that is completely about how we schedule the work. And And that's why I'm talking about it in the same lecture as the last hour. So Cilk spawn does not specify when anything executes. It only specifies whether or not it can be executed independently and in parallel. Okay. So here's my quicksort, and I changed my quicksort just a little bit so that one of the two recursive calls is now spawned quicksort. So this is the normal quicksort algorithm with exactly one change. And I drew what's going to happen, right? So now quicksort runs partition, which is a normal function, then calls spawns quicksort on the first half of the array, and then calls quicksort normal function on the second half of the array. So if I had to draw these diagrams like on the previous slide, partition happens, then we spawn one quicksort, but run another quicksort on the original thread, and each of those recurs. Each of them call partition and spawn another quicksort, and so on and so on. So this is the independent work that we have available to us. And that I put one little thing here, I changed the algorithm just a little bit to say if the size of the array is small, if begin minus end is less than some value, stop doing all this parallel stuff and just do it sequentially. Right? Because we know how expensive it can be to synchronize and communicate with other threads. So we're like, you know what, look, it's like 10 values, let's just sort it sequentially. Okay. So that's what this is. Sort sequentially if the problem size has gotten small enough that we just don't want parallelism anymore. Okay. So the idea of this programming language, and this is very high level, this is, it allows you to write parallel code very much like how we think about the algorithms, is that the programmer is supposed to tell the computer, here's where the parallel work is. And the computer is trying to figure out where or when it should run in parallel. That's the contract. Okay. So that's the abstraction. Now let's talk about implementation. So one answer would be every single time I solve Cilk spawn function, I go ahead and create an actual thread for that function. Make sense? So one possible implementation, if I gave you as a homework assignment, please go implement the Cilk compiler. The easiest possible solution that you would come up with is, oh, every time I see spawn, I will run it in parallel. So I'll just create a thread and do the work on that thread. And I showed you last 2 classes ago that if you create a bunch of threads and don't do too much work, you might be 100 times slower than if you did a good job of just creating exactly the right amount of threads. And those threads go to the list and say, what should I do next? So we're going to use a better implementation. Okay, so yes, so if we created a thread for every single one of these, our program would probably not run very fast because we want to create all this parallel work, put it all on the list, and if every single time I went to the list I spawned a new thread, that would probably be slow. So my implementation is going to be very much like what you might expect, is I'm going to create one thread for every processor, or one thread really for every execution context. So on this machine I'd probably create 8 threads, 4 times 2. And all of those threads are just going to keep going back to the list and say, what can I do next? What can I do next? What can I do next? And Cilk spawn is like putting that function call on the list. That's what Cilk spawn has actually behaved like. Okay, so I want you to consider, oh, by the way, for your programming assignment, if you look in the common directory of your starter code, like assignment1/common, or no, if you look in the common directory of the ISPC code, is that right? No, it's in the starter code. Sorry, it's in the starter code. You will see the implementation in C++ of ISPC tasks. And the way ISPC implements tasks is if, let's say you create 1,000 tasks. You create 1,000 tasks. ISBC only creates one P thread or one thread per core. And it is implemented exactly like the first half of the lecture. If you created 1,000 tasks, every thread just says, give me the next task. It increments a single counter and does the task. And all the threads keep doing that until they're done. So any performant parallel system will do exactly that. It will create exactly the same amount of threads as it thinks it needs. It will put all the work in a list, and all the threads will go to the list to get the next thing to do. Okay. So let's think about this example. Cilk spawn foo bar sync. So that looks like this. Thread spawns foo, does bar, syncs. And I'm going to use two terms here. So I want to call the thing that we spawn, I want to call it the child. And I'm going to call the rest of the stuff to do the continuation. Because that's sort of like, if you continued on in the current thread, that's what it would do. So the reason why we call it a child, it's like a child in the tree. And this is the continuation because you just keep going straight. So I'll use these terms for the rest of the lecture. So imagine you had this code, and you had a 2-core processor, 2 threads. It's an interesting question. If thread 0 is running this code, should thread 0 run foo? Or should thread 1 run foo? How should this work out? And it's kind of it's not very clear to me when I first saw this what the right answer is. Because we have 2 processors. Foo and bar can be run in parallel. The caller of foo was running on thread 0, let's say. Should the caller run foo or should it run bar? It's sort of unclear what the right answer is at this point. Okay. So it's useful to think about what happens with no Cilk at all. Let's just say it's completely serial. So I have a thread. That thread has a thread stack. We call foo. We push the continuation onto the stack. We run foo on thread 0. Come back, and the stack tells us what to do next. The stack, the program stack, is how we remember what to do next. So thread 0 has the stack, pushes the continuation onto the stack, calls foo. When foo is done, comes back up, looks at the stack, starts doing what it's supposed to do. Okay, right? But the problem with this implementation is while I'm executing foo, bar is on the stack, and thread 1 could have been doing bar, because bar and foo are independent. Foo and bar can be run in parallel. Okay, so this is bad, right? Because if it's a sequential program, I don't know that the other function can be running on thread 1. Okay, so here's what Cilk is going to do. Here's our solution. So our solution is that we're going to, for every thread, we're going to make a list. And that list is stuff that the thread needs to do going forward. So thread 0 has its stack, and whenever it sees something to do, it puts it on its own list. So in this case, thread 0 is running. It says call foo, and thread 0 says, okay, I'm going to go do foo, but I'm going to put bar, I'm going to put the continuation on my list. So that's what I drew here. So thread 0 starts running foo, but the continuation gets put on this list. And thread 1 is sitting here now going, okay, I'm just going to do work in my own list. So thread 0 has a list, thread 1 has a list. And thread 1 is like, as long as there's work in my list, I'm just going to do that. This is like when Nan and I did not want to talk to each other. Nan has his work list, I have my work list. But right now, thread 1's work list is empty. So as soon as thread 1's work list is empty, there's nothing for thread 1 to do. Thread 1 goes over and looks at thread 0's work list. and says, ah, I see that there's like, you have bar to do, but you are busy working on foo. So I'm going to go ahead and take that. I'm going to go over to Yan's list. Say, Yan's very busy right now. I'm going to take bar, and I'm going to put it in my list. So I've stolen it from Yan. So now thread 1 can just start working on the thing in its list. So now thread 0 is working on foo. Thread 1 is working on bar. And now they're running in parallel. What? Well, so in this example, yeah, I could put something up here. But thread 0 is running. It sees call foo, spawn foo. And it says, ooh, I need to put the rest of me in the list. And I'm going to go work on foo. Because this was spawn foo, the foo can be in parallel with everything else. So in how I just described it, I just described it as I'm running, I start running, I put the rest of it aside, and really it's like Yan is running. Yan sees call foo. Yan puts the rest of the work he was supposed to do on his list and starts working on foo. I'm the other thread. I have nothing to do, so I look around and say, ah, let me look at Yan's list. Yan's list has bar on it. I'm going to steal bar, put it in my list, and now I start working on it. So now we're working in parallel. Now, there was a decision to make which was kind of interesting. The way I just explained it, Yan got to the spawn, and he made the decision to start working on foo and put bar aside. He could have also decided to put foo aside and just keep working the way on the current thread. So there were two options here and how to implement this. So the first option was called run, or the first option was run child first. What I described was run foo, run the child first. We could have also done run continuation first, which is kind of interesting. And so it's also not very clear which one is better. So which one do we choose? So let me give you an interesting example. Let's look at this piece of code. So this piece of code is in a sequential for loop for I equals 0 to 10, spawn foo 0, spawn foo 1, spawn foo 2, spawn foo 3, spawn foo 4. And that will look like this, where this is the first spawn, second, and so on and so on. So if we run the continuation first, and that means put foo aside, look what happens. So what happens is that Yan will end up saying, oh, well, I'm going to put foo 0 aside, foo 1 aside, foo 2 aside, foo 3 aside. So Yan builds up this really long list. And then if I want to steal, so this is the really, really long list. If I want to steal, then I go steal one element from Leanne's list, and it's only like one element of the array. So I steal it, I go do it, and then I have to go steal another one, and so on and so on. So compare that to how it would work as if we ran the child first. So if we ran the child first, Yan would say, okay, I'm going to start working on foo 0, and I'm going to put the rest of the work aside, which is like the rest of the loop aside. So the queue has basically the rest of the loop with starting at I equals 1. So this is a lot of work. This is iteration 1, 2, 3, 4, 5, all the way to 10. So it's a little bit different. So now, if Yan's working on foo 0, I go steal the continuation, and now I'm running the loop. I'm actually running the for I equals 1 to n loop now. And if it's run child first, I get to call spawn foo 1. I start running spawn foo 1, and I put I equals 2 continuation into my list. Right? And so when Yan gets done, he's going to steal that back. And the continuation is just going to bounce around. So do you see the difference between these two policies? So in one of them, the queue fills up with a ton of data immediately. It's like breadth first search. And the second one, the queue doesn't fill up, it just bounces back around. So we will get, yeah, so thread 1 would still a continuation, thread 1, okay. So now let me look at the example of quicksort. So here's quicksort, and imagine that we've done a couple of recursive calls. So the first time we called quicksort, we spawned, so this is quicksort on 0 to 200. So the first time we did quicksort, and let's say we're run child first. So we split it into 0 and 100, and 101 to 200. So Yan starts working on 0 to 100, and puts 100 to 200 in the list. And now he's working on 0 to 100. He starts working on 0 to 50, and puts 51 to 100 in the list. And so on and so on. Right, and so you see 3 recursive calls in the list now. So does everybody see how the numbers in the list are correct? The first thing we did is we split the work into the first 100 and the second 100, push the second 100 onto the list. Then Yan keeps running, splits the work into the first quarter, 0 to 25, or 0 to 50, 51 to 100, puts 51 and 100 on the list, and recurses again and again. Right? So that might look like this. So, and now he's working on 0 to 25. Now these other processes are empty. They have no work in the list, so what will they do? They're going to go say, hey, I need some work. So now here's an interesting question. Thread 1 needs work. There are 3 pieces of work in this list. Which one should it steal? So I hear top. So what is your answer? Why do you believe the top one is the best one to steal?
Since the task is split into many small species, but
Yeah.
the top one is the big.
Because, so we should think about this really as a stack. And we're pushing, it's not a list anymore. It's really every time you get new work, you push it onto the queue, or you push it onto the stack. And what you have observed is that it makes a lot of sense, is if I'm going to spend all this time walking over to Yang, bothering him, bothering myself to get new work, I should probably get a lot of work. And if this is in stack order, the biggest piece of work is on the top. So one good reason to steal the top is that whenever I bother somebody, I have the lowest overhead because now I have a lot of time before I need to bother anybody again. Another good reason is actually it means we're now doing the biggest thing first. We're doing the biggest jobs first. So we learned just at the end of the last hour that it makes sense to do the big jobs first so that things don't get so bad. That's another, it's not as important, but it's kind of interesting. And then the last thing, which I won't talk about, is that Yan is working here. If Yan needs new work, he's going to grab this part of the list. Because if you grab this part of the list, you're running in the original sequential order. This is the call stack. So you have high locality and high cache behavior on this thread. So he's going to pull the work out of here. I'm going to steal the work out of here. So he runs very much as efficiently as if it was sequential. And he's working on that side of the list, I'm working on this side of the list. And so we actually don't have to interfere with each other nearly as much as you would think. So as long as that list is pretty deep, I just pull this, and it doesn't interfere with him at all. So that's pretty interesting, very elegant property of a doubly ended queue. For if you put work on the queue, you take the work that you just put in off. You take small things off. If you want to steal work, you steal from the top. And next lecture, Yan will talk a little bit, about how it's possible to prove that if you do this, and that if you randomly pick which person to steal from each time, you can prove bounds on how expensive your computation will be or how well balanced it will be. Okay, so let's kind of go through this whole thing. Thread 1 needs work. So it steals. And you were right, I think it should steal this item. So thread 1 stole the biggest thing. Thread 2 steals the next biggest thing. Over here. Now, thread 1 starts working, thread 2 starts working, and it's performing recursion, so it starts pushing the continuation onto its stack. Right? So that doesn't matter right now. And then they're all working. So notice that there's no communication anymore. They're continuing to recurse. Every time they recurse, every thread finds new parallel work. When it finds new parallel work, it puts one of the options on its stack. And we get to a place that looks like this. So now, no communication, everybody's just building up work to steal, they're doing their own thing, and then only at some point when one of the workers runs out, or there'll be a steal again. But hopefully that's not very often, because every time there's a steal, you steal from the top. So if you have a recursive program, a divide and conquer algorithm like quicksort, it actually is a very elegant way to write code. So here's a for loop. So this is the example I gave you before. For I equals 0 to 10, this is a completely parallel for loop, right? Every iteration can be done in parallel. And I showed you this graph. The problem here is that if we run either way, if we run the child first or the continuation first, if we run the child first, the continuation bounces back and forth between me and the end. And so the parallelism gets revealed sequentially. If we run the continuation first, there's one thread generating the parallel work. So if this is a system with like 100 processors, it might take a while for that one thread to create all the work for other processors to start working on. Whereas if I wrote the exact same loop in a recursive way, which says, take the 10 iterations and divide it into the first 10 and the last 10, then all of a sudden I start generating iterations in parallel, which is pretty cool. So the for loop in Cilk is actually implemented as this while, this recursive while, because what happens is it splits into two pieces of work. Both two processors start working in parallel, and then they split into two pieces of work. And now four processors are working in parallel. So the work gets created much, much faster in this version. So if you saw a parallel for loop in Cilk, Cilk has a parallel for loop. It's actually implemented under the hood like this, which is pretty cool. Okay. All right. So let's talk very briefly about implementing sync. 5 minutes? 5 minutes, right? Okay. So the only thing I told you, well, I told you almost everything. I told you how to distribute work. So the work distribution is very easy. Every time you see spawn, you put the rest of your work on your queue, and you start doing the call with your spawn. If you ever run out of work, steal the time. That's the whole algorithm. Sync is a little bit more complicated, because sync means I have to wait for Yan to finish something, which is a little bit different. So let me talk very briefly through this. Okay, so let's consider this part of the code just a block of code. Now I'm just going to call it block A to be very useful, to be very simple. And so block A creates all of these independent spawns. And the sync at the end here, this thing can only return when all of those spawns are done. But it can be a little tricky to know when all the spawns are done, because they might have been stolen by other processors might be working on it. It's a little tricky to know when they're done. So let's think about how I would implement sync. So imagine that thread 0 is running. It is in the run child first. So it's working on foo 0, and then it works on foo 1, and then foo 2, and foo 3, and foo 4, or whatever. So it gets to the end of foo 9. It's about to finish the last foo. If no other thread has stolen work, there's no difference at all from sequential programming. No difference at all. This is just the stack. And we just pop the stack and we go. So Cilk sync is nothing if no work has been stolen. So if no work has been stolen, this thread did all the work. And if we get to here, by definition, all the work is done, and we can keep going. So it's only complicated if other processors have stolen work. And we need to do a little bit of bookkeeping to get that right. So let's say that the first thread is working on foo 0. The continuation is the rest of the iterations. I equals 1 through, okay. So thread 1 will steal. And when thread 1 steals this item, I'm going to put a marker in my list. And it's going to say, aha, this has been stolen. And so now this item is sitting over here in this other guy's list. But I know it's been stolen. And I'm going to keep a counter over here, which says for block A, this is the number of calls that have been created, that are spawned, that are being worked on. And it says 1 right now, because there's one person working on it. And out of those calls, 0 of them have finished. So I'm keeping 2 numbers. I'm keeping a record of how many things I have created, and I'm keeping a record of how many things have finished. So now when thread 1 starts executing the second iteration, let's say it starts working on foo 1, notice that now spawn is 2. So it's going to update, we're going to update this counter. So now spawn is 2 and done is 0. And this can just keep going, is that so when thread 1 finishes, thread 0 finishes, excuse me, then all of a sudden done becomes 1, and of course we've involved other threads, and so there's more stealing. So let's say we get to the very end, and we get to the very end is that all processors are done with their work. Thread 2 is working on foo 9. Notice that spawn is 10. Done is 9. Whenever this thing completes, then we notice that spawn is 10 and done is 10. And then we can just continue on. We can send the continuation back. Okay, so that it's done. 10 are completed, 10 are done. And then we can just start working the sync. That means that the sync is done at this point. And now we can continue, this thread can continue on after the sync and start calling upon it. So there's just a little bit of extra work that the code has to do to get this right. And that if nobody does any stealing, it behaves just like normal function calls. And there's very little overhead. If work has been stolen, we have to pay overhead to update counters and done markers and things like that. But we're willing to pay that overhead because if we didn't steal, we would have had workload imbalance. So it's okay to have some overhead. And I think that we're almost done, so I might stop there. Maybe I'll just summarize the last slide here. So the scheduler in Cilk, which is a very beautiful, elegant system, it uses what's called greedy join scheduling. Is every thread will pull work from its own list. If its own work from the bottom of its own list. If it ever runs out, it chooses a random other worker and pulls from the top of its list. And the idea is that if you pull from the top of somebody else's list, you're pulling the largest possible thing so that you communicate as little as possible. And then you only communicate with another thread when you run out of work. So unlike the simple work queue example that I gave you at the start of the class, it's not like I have to sync up every single time. We only sync up if I would have otherwise had nothing to do. So that's basically the Cilk scheduler. And next time we will have Yan give a talk on being a little bit more formal about reasoning about some of the bounds of the schedule. Like this, the algorithm that I gave you is provably optimal. We will not prove it, but it is optimal in terms of workload bounds. Okay, I think we're good. Oh yeah, one more.